Hi and welcome. I'm trying to learn cytology. Today, secondary active transport, and after we've done what we're going to do hip training. And if you participate in the hip training, it's at your own risk. Secondary active transport. In secondary active transport, the energy stored in a sodium ion or hydrogen ion concentration gradient is used to drive other substances across the membrane against their own concentration gradients. So for whatever reason, there are sodium ions and hydrogen ions, and furthermore have the energy stored in them for whatever reason, and that helps to bring substances through the membrane of substances, even if it is against their own concentration gradient. Because sodium ion and hydrogen ion gradient is established by primary active transport. We said sodium comes out, whatever. So sodium, because sodium ion and hydrogen ion gradient is established through the primary active transport, secondary active transport indirectly uses energy obtained from the hydrolysis of adenosine triphosphate. So that was just said by the primary active transport. There is just, for whatever reason, some sodium, and on the inside of the cell it comes to the I think it sits to the inside the cell, and then it comes there, and that causes we are just binding there, and then it's triggered the adenosine triphosphate. Okay, we are just binding there, and then comes the adenosine triphosphate. It binds up with some phosphor, and it becomes an adenosine triphosphate. I think it is adenosine triphosphate. No, it is adenosine triphosphate. How do I say it? It was ATP. Now it is ADP. It gets one phosphate there, and that changes the shape of it, and the sodium comes out, and then some potassium comes in, the phosphate, the binding of potassium ions causes the pump protein to release the phosphate group, which again causes the shape of the pump ion to change, and now the potassium comes out again. So that was after the sodium has docked onto the channel changing thing there, adenosine triphosphate, which had bound up the phosphate to make ADP, whatever it is, and it changes the shape of it. The phosphate was released and back again. And here was adenosine triphosphate used to change the shape to get the sodium out. And because now that sodium is used to bring again in whatever, indirectly the adenosine triphosphate is used. The sodium pump maintains a steep concentration gradient of sodium across the plasma membrane. They mean that by the primary active. As a result, the sodium ions have stored a potential energy just as water behind them has potential energy. So they have potential energy because the sodium ions, they seem to come by themselves, want way to come back in again. So just like water, they just want to come back in again. And it is just, they have the potential to go back in again because they're gonna do that. They are just flowing over. They have potential energy. So they have energy through being in the place. It's just called like that. People see just there is a ball lying on a big hill, if I understand it correctly. I try to make it now as easy as possible because I think I understand what they all mean with it. They're just saying there is a ball lying, and that ball could now run down the hill. So, and running down that hill, it would be energy. It has an energy. If it would impact something, it would then make a sound or something if it comes against the wall. It has strength in it. So potentially has its strength. If it would roll down, it has strength. So potentially, it has energy. That is all what I say. There's sodium, and it could go, and it is doing that. So it has potentially energy. As a result, the sodium ions have stored or potential energy, just as water behind the dam has potential energy. It is there, and potentially the dam could break and the water is flowing out. Accordingly, if there is a route for sodium to leak back in, some of the stored energy can be converted to kinetic energy. It is just the ball lying there. Kinetic energy just means it is moving. To stop it, someone has to put quite a lot of energy in to stop the ball. If it's a big ball, whatever. And so it is just there. It has potentially energy should it roll down. And if it is rolling down, it is moving and has an energy. To stop it, someone would have to put energy into stopping it. So it has been moving energy, kinetic energy. in essence, converted into energy of motion and used to transport other substances against the concentration gradient. So there is our football lying on the hill, and inside of the football is air. And if a ball has potentially energy because it could potentially roll down, if it is rolling down, it is moving, and to stop it, someone has to put energy into it. So itself has moving energy, kinetic energy, because it would have to be stopped. And inside of the ball is air, which is accidentally, or whatever the right word is, drawn with it down. In essence, secondary active transport proteins harness the energy in the sodium concentration gradient by providing easy routes for sodium to leak into cells. It's the same what I just said. The protein acts as a coupled transporter by simultaneously binding to sodium and other substances and then changing its shape so that both substances cross the membrane at the same time. Do we still talk about the same thing? Accordingly, if there is a route for sodium to leak back in, some of the stored energy can be converted to kinetic energy and used to transport other substances against the concentration gradient. Do we just mean because they move in? Let's see, we understand what we're saying, maybe we're going to get it later. In essence, secondary active transport proteins harness the energy of a sodium concentration gradient by providing easy routes for sodium to leak into cells. So, I said within the first part that it is like a sinking ship, that all the time the sodium is coming back in. We were wondering in the previous two parts why Cyankali kills within a few minutes. Because it seems to stop that it can be where the primary active transport is happening. And then we had one clue that all the time the sodium is leaking back in. And so it would mean there's not just a little bit stopped some doing, but it's also directly like a sinking ship where water is pumped out, directly it is stopped, and all the time sodium is leaking into the cells. So if a Cyankali would be in the body, we don't know, this is just interpreted between the lines. If it would come in, it would directly flood the cells. So that would be an explanation why a person dies so fast from Cyankali. But we have no idea, it's just read between two lines. And nobody's saying here that might be intentionally, that the sodium can so easily leak back into the cells because it is taken with it nutrients. Would be nice to have an example, because I'm certainly there is some where people intentionally allow rivers to flood because they're bringing then fruit, what is the word? Something that makes it good grow. Fruit or whatever, sediments onto the sides of it. Would be interesting if there's anywhere an example where people intentionally allow a river to flood so that it can take the flood nutrients onto the fields next to it. The protein acts as a coupled transporter by simultaneously binding to sodium and another substance and then changing its shape so that both substances cross the membrane at the same time. So who is now the secondary? I think that could be the thing on top. Let's read the sentence again and then we're going to look closer to explanations. The protein acts as a coupled transporter by simultaneously binding to sodium ions and another substance and then changing its shape so that both substances cross the membrane at the same time. Plasma membranes contain several antiporters and symporters that are powered by the sodium gradient. In most body cells, the concentration of calcium ions is low to the cytosol because sodium or calcium antiporters let sodium ions enter the cell while ejecting calcium ions. Let's take one look at the graph here, or at the illustration. Figure 3.12. Secondary active transport mechanism. A. The antiporters A. Antiporters carry two substances across the membrane in opposite directions. And B. Symporters carry two substances across the membrane in the same direction. I don't understand the symporters. Why should we do it? And how should we do it? And what is the good thing to have two at the same time? Because they're binding together, that was it. Secondary active transport mechanism used with energy stored in an ionic concentration gradient, here for sodium ions, because the gradient is maintained by primary active transport pumps with hydrolyzed adenosine triphosphate. Secondary active transport consumes adenosine triphosphate directly. Cytosol when sodium, and the sodium comes in and one goes out. And by these importers, two come together, and because they're bound together, did we say? Okay, we don't have time. If you were here for cytology, you can go directly to the next part. Where we're gonna read on what was also written to the secondary active transport and look at the whole thing again. If you stay here and participate in the hip training, then it's wird die Augen gehen. Have your feet standing together. Open with one foot to the side and the other foot. Here's toes. And begin again. This time stay down in the knees. And up. Legs a bit to the side, down into the knees, flex, press together, straighten one leg. Bend it again, the other leg, straighten it, bend it again. Up. Back to the side, down into the knees, flex, press together, over to one side, and to the other side. Middle, and up. And one leg up, leg to the side, really good. Middle and down, the other leg up to the side, really good. Middle and down. And one leg up and straighten it and pull the toes in, up and point down, out. Pull the toes in, up, point down. And the same with the other foot. Straighten the foot, up, point down. Between hip training, not leg training. Why do we have some exercise? Leg out, pull the toes in, foot to the left and right. Left and right. Our foot out, pull the toes in, right, left. That's all. And stay good. One foot to the side, lift this foot off the ground, place it again onto the ground. And with the other leg to the side, up and down. And one hand on tummy, one on lower back, one leg with a straight line up. Try to bring the leg higher and pull the toes in. Control the hands but you don't fall back. Try to bring the leg higher. And pull it up. And on the other side. Straight leg, try to bring it higher. Pull the toes in. Control the hands but you don't hold back. Leg high up, pull the toes in. And up. And stand good. One leg up. Is up, side. On the other side. Leg up, side. And stand good. Turn over to a standing leg. Down into the knees. Control it. Concentrate it slowly over to the other side. And up again. Change the leg. Stand good. Turn over. Down into the knee. Concentrate it over to the other side. Stand good and reach always with the heel to imaginary 90 minutes intervals on an imaginary dial of a clock. And the same with the other foot. 12 o'clock, 1:30 and 3, 10:30 and 9, 8:30 and 7, 4:30 and 3 o'clock. And one leg up and down. Other leg. Stand good, arms to the side, one leg up, bend in front, leg up, down again. And pull the knee in and out. And down the same with the other leg. One leg up and down again. Pull the knee in and out. Leg into the middle. next to the sides, leaving it around. In and up. In and close relax. And out. That was the hip training. I thank you very much, and until next time.